Let's pick up then with Hanley, Shogren, and White's Chapter 8, all about conflict and cooperation. I will say this is covering one of my favorite topics in economics, that's game theory, and they're applying it then to the economics of the environment. So one thing I will say is that they have more specific applications in the textbook, so check out Chapter 8 of Hanley, Shogren, and White's book if you want to see those applications. I'm mostly trying to fill out some of the details of the theory that they kind of gloss over, and also provide some additional applications. So, overview of what we'll talk about here in this video. First, we'll look a little bit at prisoners' dilemmas and relate them to environmental issues. Specifically, we're going to look at externalities and how they would connect. Then we'll take a look at cooperative game theory, which is a topic that I actually usually don't cover in my introductory economics classes, but cooperative game theory is very useful in helping us to understand things like transboundary pollution control and environmental agreements. Although I will say that transboundary pollution control, we're going to go kind of light on that. More of the details for that would be there in the textbook. All right, so let's talk about the prisoner's dilemma. The prisoner's dilemma is probably one of the most famous ideas coming out of game theory. So let's get into why that is. Now, but before we talk about the prisoner's dilemma in detail and kind of the conclusions of it, let's look at the basic assumptions. All right, so the first assumption is that rationality is common knowledge. What that means is that first, all of the players involved, usually we'll just deal with two players, right? So both players are pursuing their own best interest, so they're self-interested. What we mean by rationality is that fact that they are self-interested, and also the fact that they will think through the consequences of the game. They're going to try to reason fairly well. The common knowledge component of it is that not only are both of our players self-interested and also reason through the game, but they know that about each other, right? So player number 1 knows that player number 2 is self-interested and will reason through the game, and player 2 knows that player 1 is self-interested and will reason through the game. And not only that they know that about each other. So player 1 knows that player 2 knows that player 1 is rational, and so on. Right? A second basic assumption of the prisoner's dilemma is that there is no possible way for any agreements that are made ahead of time to be enforced. So no enforceable agreements are possible. Okay? And then finally, we assume that this is a one-shot game, that it is just played once, we see the outcome, and that's it. Right? So we can't have any additional, say, consequences or behavioral responses coming after the game is played. So here's a classic prisoner's dilemma. So we have Bonnie and Clyde, and they are committing crimes together, and then they get caught. So when they get caught, the police take the two of them, put them in separate rooms, and try to undergo a plea bargain. So each of them is given this deal. That is, if both players confess, that is, if both Bonnie and Clyde separately decide to confess, then they will each be put away in prison for 5 years. On the other hand, if neither of them confesses, then the police do admit that their evidence isn't particularly strong, right? But they can get them on lesser crimes. They can still put them away for 2 years apiece. On the other hand, if one of them confesses and the other doesn't, then whoever confesses is being offered a plea bargain, so they'll be allowed to just get off scot-free. On the other hand, the one who does not confess will now have mountains of evidence against them and will therefore be able to be put away for a long time. That's 10 years in this example. So let's reason through what Bonnie and Clyde would decide to do. Right. Now remember, they're in separate rooms, they can't communicate with each other, so there's no good way, right, for them to really commit to one tack or another, or to communicate with each other to make a deal. So Bonnie is forced to think about her decision, right, not really knowing what Clyde is going to do, so having to reason through each possible case. Right. So Bonnie says, right, if Clyde confesses, then I, as Bonnie, can also confess, in which case I get 5 years in prison. On the other hand, I, as Bonnie, could not confess and get 10 years in prison. Well, so given that Clyde is confessing, Bonnie would much rather confess, getting 5 years, than not confess, getting 10 years. And so I'm just going to draw an arrow here to indicate that. Meanwhile, if Clyde decides not to confess, if Bonnie believes that Clyde is trustworthy, then Bonnie has the choice of either confessing and thereby spending no time in prison because she helped put Clyde away, or not confessing and getting 2 years in prison. Well, I confess I've never been to prison. Maybe 2 years might be fun, but I suspect not. Right? So Bonnie says, I would rather spend no time in prison than 2 years. So again, would decide that confessing is the best option. So what we've just figured out is that Bonnie, as long as she is rational, will decide that she would rather confess than not confess, because confessing will definitely give her a lower prison sentence or a lesser prison sentence than she otherwise would have had. Clyde follows the same reasoning. If he figures out that Bonnie is going to confess, he realizes that if he doesn't confess, he's going to be in prison for 10 years. On the other hand, confessing would allow him to only spend 5 years in prison. On the other hand, if he believes that Bonnie will not confess, Clyde still knows that if he confesses that he would have no time in prison, which is certainly better than 2 years. So Clyde, very much like Bonnie, has every reason to go ahead and confess. So we end up with this outcome, right? Where both Bonnie and Clyde decide to confess, and as a result, they're both in prison for 5 years. Now you might object and say, but this doesn't really make sense, because wouldn't they, after all, be better off if neither of them confessed? And that's true, and that is exactly where the prisoner's dilemma comes from. That is, individually, they each have a really strong reason to do what they did, but the outcome, it turns out, is pretty lousy. Right, so the results we get is that we know that collectively, neither of them confessing would provide the best outcome overall, but individually, it's very rational for them to confess in any case, so both of them decide to end up confessing. So it's this conflict between what is individually rational and what is collectively optimal that really makes the prisoner's dilemma an interesting case for economists to talk about. So let's look at a few applications for game theory that are relevant to environmental economics. First would be externalities. Right? So externalities would be a case where benefits or costs of a decision that I make are accruing largely to other people. Right? So for example, if I make some kind of decision that's going to be very beneficial to people other than myself, right, then I should do it according to what is socially optimal. It's going to be good for society as a whole if I do it. But on the other hand, if I'm not the one that sees those benefits, I'm less likely to do it than I really should be. Right? And here we can think about things like, for example, the decision to raise honeybees, right, in an area where there are lots of orchards. Right? In that case, raising honeybees, a lot of the benefit of it isn't the honey you get, but rather is the fact that honeybees are very excellent pollinators, right, for fruit trees. Right? So a lot of the benefit would accrue not to you as the owner of the bees, but rather to the orchard owners. Right? So as a result, what we'd see is that fewer people raise bees in these areas than would actually be optimal. Another case would be what we call public goods. Right? So this is actually very similar to that positive externality that I just mentioned. Right? So with public goods, remember these are goods that are both non-rival, that is, one person's use doesn't get in the way of another person's use, and also non-excludable. That is, you can't prevent someone from getting the benefit if they decide they want it. So the issue with public goods is that if I decide to provide it, so I pay for it, I pony up the bill to make sure the public good gets provided, a lot of that benefit is going to go not to myself, but to other people who decide that they want to use this good. And as a result, it makes sense, right, for me not to pony up the money myself to provide the good, but to wait for someone else to do it, and then I can free ride on what they've decided to do. Right? Everybody facing those same incentives, right, means that nobody ends up providing the good, or at the very least, far less is provided than really should be. Another example would be common pool resources, or what we call the tragedy of the commons. This is very similar to a negative externality. So here we can think about things like, say, fishing in international waters being the classic example that I like to use. And so this is a case where the good is rival, that is, my use will interfere with other people's ability to use the good. There are only so many fish out there in the ocean at any particular point in time, right? But it's non-excludable. It's fairly difficult, right, to prevent me from going out and capturing these fish. Right, so what is perfectly rational for me to do is go out and try to catch as many fish for myself as possible, right? This is a perfectly reasonable thing to do, despite the fact that it's creating costs on others, because it's making it more difficult for other fishermen, right, to catch those fish. So it's individually rational with these common pool resources for us to overuse them, right? And as a result, we can end up actually hurting the ability of fish populations to maintain themselves, and they could actually decline over time because of overfishing. Right, so these are all cases where game theory would come in. Right? So externalities, public goods, common pool resources, we can get the idea of the problems with these by looking at game theory. Let's look then at a specific model where we can see how game theory would work in practice. So here we have a negative externality model. Right? So we're really thinking about the damage done by pollution. Now we're going to keep it very simple, just two polluters. Right? The damage done by pollution to any one of them is based on the total pollution done. We take that total pollution, that is pollution from polluter 1 plus pollution from polluter 2, and we'll square it. This squaring captures the fact that the amount of damage done by pollution, right, tends to accelerate the more pollution there is. In effect, if you have a small amount of pollution, a small amount of damage is done. If you have twice as much pollution, it's more than twice as much damage that is being done. Abatement cost, then, is going to be all based on 30 minus the amount of pollution that a particular polluter emits, right? So let's just think about polluter 1 here. If they're allowed to pollute 30 units, if that is the decision they make, then they don't have to pay any abatement cost. We'll just say that if they normally produce without taking any kind of precautions to reduce the amount of pollution that they're creating, then 30 units of pollution is it. Right? On the other hand, they could pollute less, but it's going to cost them something to do it. And the further they cut their pollution, right, then we'll have this accelerating cost, which is captured by the square there. And this applies both to polluter 1 and polluter 2. Right? So for polluter 1, we'd have P1 in the formula. For polluter 2, we'd have P2 in the formula. Now, the goal is to choose the level of pollution that is going to minimize, right, the total cost. So first, let's look at the social optimum. Right, so for the total cost for society as a whole, we would take account of, first, all of the damage done by pollution itself. So that would be that first term, 2 times P1 plus P2, in that quantity squared. This is capturing the fact that this pollution, like the damage that it's doing, happens not just to one polluter, but to both of them. That's why we multiply by 2. But then the cost would also involve the abatement costs. So we have two terms here, right, capturing the abatement cost for polluter 1 and also for polluter 2. Now when we do the math, right, I have here, right, some of the first order conditions, right, for us to minimize this. You can walk through and do all of the math if you wish, but what you're going to end up with is the result that to minimize the total cost, what you'll end up with is that both polluter 1 and polluter 2 should pollute the same amount, and that amount is 6 units. And so they're actually going to engage in significant decreases of the amount of pollution they would create below this 30. It's actually, they're going to abate 24 units and only pollute 6 each. The result of this is that there would be a total cost for society as a whole of $1,440. Now, in order to check this optimum, what I wanted to do is just see what happens if I adjust one of the levels of pollution just a little bit. Right? So we know that if say polluter number 1 is polluting 6 and polluter 2 is polluting 6, our total cost is $1,440. Right, so what if we take polluter 1, have them produce just a little bit less pollution, right, so push them down to 5. In that case, the cost rises to $1,443. And if we push them a little bit higher, say up to 7 rather than 6, it also increases to $1,443. Right, so this would help us to confirm, right, that $1,440 is the lowest cost that we can possibly achieve, and that is achieved when both polluter 1 and polluter 2 are each producing 6 units of pollution. Okay, so we've confirmed the optimum. If we break this up, that means that the cost for the two of them is going to be $720 each. Now I think about the individually rational choice. Now in this case, right, the amount of damage that a particular polluter is experiencing is just their own, right? Their own damage, right? So that's P1 plus P2 squared. We don't have to multiply by 2 here because I don't consider the effects on the other polluter, just on myself. Similarly, I would only look at my own abatement costs. So both of these terms here would again be added together. And we're just looking at polluter 1 in this case, right? So what we find out, we go through, we solve the formula using some calculus, and we find out that if we look at polluter 1's problem and polluter 2's problem, right, solve that system of equations, we find out both polluter 1 and polluter 2 would want to create 10 units of pollution apiece. Right? So it's still well below the 30. Right? So we would have individually the polluters taking some big steps to cut their level of pollution, but it's really because they want to prevent the damage done to themselves. They're not concerned about society as a whole. Right, so the result here is that each individual would end up having a cost of pollution of 800 total once you add the damage that's being done both by themselves and by the other, and then also the abatement cost that they themselves are taking on. The result then would be a total social cost of 1600. Now note this social cost of 1600 is greater than if we made the collectively optimal choice of 1440. So you can put all of this into game theory using a game matrix, but we'll get to that. Right. First, let's just double check rationality. Right, so look at these individual levels of 10. So let's suppose that, say, polluter number 2 is polluting 10. Right? I'm polluting 10, my cost then would be 800. If I decide to decrease a bit to 9, my cost goes up to 802. If I increase a bit to 11, my cost goes up to 802. Right? So if they're at 10, I also want to stay at 10. Right, so end result, we have 20 pollution versus 12, 1600 cost versus 1440, and that is. Here's where we can look at things through the game matrix perspective. So what I've thrown out here is we have polluter 1 and polluter 2. They're really choosing between two choices. Right? One would be what we know as the collectively optimal choice of each polluting 6. The other would be the individually optimal choice of 10 units of pollution. And then we think what happens if we have kind of a mix. Right? So one pollutes 6, the other pollutes 10. Right? So I have all of that laid out here in this game matrix. So let's go through and look at it just like we did with Bonnie and Clyde. So what we find out is that polluter 1, they don't know for sure what polluter 2 is doing. Right? After all, there's no way for them to make any kind of enforceable agreement. Right? Even if they make some word-of-mouth agreement, there's no reason that they should necessarily believe each other. They could just lie to each other and go home and do what they want. Right? So let's look at what polluter 1 would decide to do. If they believe that polluter 2 is polluting 6, that puts them in the left column. In that case, polluter 1 can either pollute 6 as well, and that would be a $720 cost, right? Or they could pollute 10, and that would lower their cost to $656. After all, it turns out that most of the damage being done by those additional 4 units of pollution, right, roughly half of the damage is being done to polluter number 2. Meanwhile, all of the savings, right, from not having to abate so much is going to polluter number 1. Right? Meanwhile, if polluter 1 believes that polluter 2 is going to go with the higher level of pollution of 10, then polluter 1 knows that if they still pollute 6, that's $832 of cost they're going to have to pay. On the other hand, if they pollute 10, that's only $800. Well, $800 is a better cost than $832. So polluter 1 makes the decision that it doesn't actually matter what polluter 2 chooses between these two options, that polluting 10 is the better choice. And polluter 2 faces exactly the same choices, exactly the same payoffs, so they would decide that if polluter 1 is going to pollute just 6, polluter 2 would rather have a $656 cost than $720. So they would pollute 10. Meanwhile, if they believe that polluter 1 is going to pollute 10, which we figured out they will, then polluter 2 would rather have an $800 cost than $832. So this confirms that individually they have every reason to go ahead and pollute 10 each, despite the fact that that gives us a worse outcome overall and a worse outcome individually than if we could find some way to have both of us just pollute 6. So this would be a classic case of a prisoner's dilemma, where we have a really strong reason to do what we did for individual reasons, but the individually rational outcome is not what is collectively best. So then what can we do to break the prisoner's dilemma? So this really comes back to those original assumptions. So the first assumption, remember, was about rationality. We're not going to touch that one. But the other two were that there's no way for us to enforce any agreements, and also that it's just a one-shot game. So what happens if we break those two assumptions? So what if we had a way to repeat this game over time? So polluter 1, polluter 2, they make a decision, they observe what happens, and then they come and they have to decide what they do the next year, and the year after that, and the year after that. Is there some way they can use this repeated nature of the game to change what the outcome is? It turns out the answer is yes, and we'll get to that in a minute. Similarly, what if they had some way to come up with an enforcement mechanism? Might that possibly be something that could help them to get to a better outcome? It turns out, again, the answer is yes. And again, we'll see how they could possibly do that. So let's start by thinking about repeating the game. So in this case, what we've just opened up is the possibility that players can respond, right, to a particular round's strategy in future rounds. So that allows them to reward good behavior in the future and to punish bad behavior in the future. A couple examples of that. One is what we call a tit-for-tat strategy. A tit-for-tat strategy is basically a copycat strategy. So whatever you did in the previous round, I will do this round. Right? So if you were loyal to me in the previous round, I will be loyal to you in this round. If you betrayed me in the last round, I will betray you in this round. Right? A second strategy is what we call a trigger strategy. It's a bit more extreme, and the way that works is that as long as you have good behavior in the previous rounds, I will also have good behavior in future rounds. But as soon as you show bad behavior, then I'm going to punish you for the rest of the time we play the game. So it's a bit more punitive. Generally speaking, tit-for-tat does perform somewhat better than trigger strategies, although a trigger strategy is a good way of showing how the logic works in allowing us to actually enforce a particular outcome. Right, so here's just an example of how tit-for-tat could work. Right, so the only real decision they make, right, so we assume that player 1 and player 2 have both committed, right, to playing a tit-for-tat strategy. So the only real decision they make is what to do in that first round. From that, everything is just copycatting whatever happened in the previous round. Okay? Right, so let's actually start at the bottom of this slide. Right, so if both of them decide to play what we knew were the individually rational strategies in that one-round game, that is to pollute 10, in that case, we end up with, say over the course of 4 rounds, just as an example, a total cost of 3,200. And let's just say the first player is thinking about whether it makes sense for them to play 6 instead in that first round, right? Because that would induce, right, the second player to play 6 in the second round, right? So we're looking at changing, right, from the bottom line up to this middle example, right? And what we find is that yes, right, player 1 will take a hit in the first round as they're now having to pay 832 rather than 800. But they're rewarded for this in the second round when they only have to pay 656. Right? So over the course of these 4 rounds, right, their total that they have to pay is now 2976 rather than 3200. Right? So given the choice, player 1 would say, well, it makes sense, right, for me just to start by playing 6. Even though it's going to hurt me in the first round, it will pay off over time. Right? As long as we have at least 2 rounds, this is going to be better for me overall. Right? So they would decide to start with 6, right, rather than with 10. Then we imagine player 2 gets to thinking, and okay, if the first player starts with 6, does it make sense for player 2 to also play 6? Right, so instead of here, we're going to look at now the top example. What we find out is that player 2 are trying to avoid being punished, right, in that second round by playing 6 in the first round. If they both play 6 in the first round and then play tit-for-tat, then they both play 6 in every round. So this would be the socially optimal outcome, and it gives a total cost of 2880, which is better than the 2976. Right? So player 2 would decide, well, knowing that the first player is going to start with 6, I will also start with 6. So we end up with a good outcome. So we just did, by implementing this tit-for-tat strategy, right, is convince the players, because they want to avoid future punishment, that convinces them to actually play nicely in every single round, as long as there's a future round that might punish them. Here's an example of a trigger strategy and how it works, right? So in this case, what we imagine, right, we're comparing what is, again, socially optimal, and I'm just going to look at the case where player 2 is thinking about deviating from that, right? So that they would have a better, right, first round, right? So they're only going to have to pay 656 in the first round instead of 720, right? Well, with the trigger strategy, what happens after that point is that the first player says, well, in that case, I'm just going to play mean from here on out. Right? We're just going to play 10 all the way out. And what that ends up with is our total costs here, right? They're unbalanced, right? But they're both over 3,000. Right? Whereas if they had just played it nicely from the beginning, then we're talking about 2880 as being the total cost at the end of those 4 rounds. Right? So with the trigger strategy, again, right, there's every reason for you to go ahead and play nice every round, as long as there's some way for you to be punished in future rounds, which is what a trigger strategy does. So I'm going to just make a couple observations of this idea of repeating the game. Right? The first thing is that it will require that there's always the possibility of a future round. Right? If there isn't the possibility of a future round, if we know that this is the last round, then there's no reason for me not to behave badly, because there's no way they can punish me in the future. Right? So there always has to be some possibility of a future round in order for there to be this possibility of future punishment. Now, one thing I would say is that it doesn't have to be a certainty that there's going to be a future round. Even just the possibility, as long as it's a strong enough possibility, will be enough to convince people to tilt more toward playing nicely. A second thing that this requires is that players actually care enough about future payoffs. That is to say, that discounting, which we've talked about before in the course, is not too severe. After all, we know that future payoffs are not treated the same as current payoffs. We discount them somewhat. So if it turns out these future payoffs are either very sharply discounted or are very far in the future, then it may be that repeating the game won't be sufficient. So it's important that we repeat this game in a way that is expected that the repetition will continue over time, and also that the repetition happens soon enough that punishments can come through fairly quickly, that people would actually care about those punishments. Now let's look at an enforcement mechanism and how this would work. So suppose that these two players, they do get together and they agree that they're each going to pollute 6. And this is not just empty words or cheap talk, being the phrase that we like in game theory. Instead, they create a mechanism that will punish anybody that decides to violate it. So specifically, anyone who violates this agreement has to pay a $1,000 fine. So their cost would be not just the cost of the pollution damage plus the cost of abatement, it's also this cost of a fine if they pollute any more than 6 units. So if we go through and we solve this game, I think we can do this one fairly quickly. Player 1 finds that for them, in either case, it would save them almost 1,000, but not quite 1,000, to go ahead and choose pollution of 6, and player 2 does likewise. So in order to avoid the fine, they find that it's worthwhile for them to go ahead and pollute just 6, even though without that fine, they would be very tempted to go and pollute 10. So that's the idea of the enforcement mechanism. Effectively, what we're doing is taking these payoffs from each of the possibilities, and we've changed them. We've now introduced an additional cost if you make a choice that is collectively bad. Now, in order for this enforcement mechanism to actually work, what we need is 2 things. The first is that it has to actually be enforceable. If there's no way for me to actually collect this $1,000 fine, then it doesn't actually mean anything. So that would be cheap talk. So we can make these threats if we wish, but the threats don't by themselves do anything. A second is that any agreement we make needs to actually be stable. This is where cooperative game theory is going to come in. Really all that means is that each of the members that signs into this agreement will actually continue to be a part of this agreement. They find it worthwhile to do that. Now, I think it's fairly easy to show that in the previous case, they would definitely want to continue being part of this agreement, because if it falls apart, we're looking at individually their costs going up to 800 even without an enforcement mechanism, as opposed to only being 720. So this would be a case where this agreement would in fact be stable as long as they could make it. Now, I want to go back to Elinor Ostrom's principles for common property. So this was something that you may recall from case study number 1, and I pulled these points from case study number 1. And so Elinor Ostrom looked at this problem of game theory and prisoner's dilemmas, and specifically how it applies to the management of common property. So we have this issue, we mentioned overfishing earlier, that if we have common property, that people are going to tend to want to overuse it. So the question is, how do we prevent that from happening? And you all had to do case studies about this and looking at specific cases and how these principles arise. But let's go ahead and go through these now, and I want to try to match these up with the game theory concepts. So first, we need some kind of clear boundaries. It's obvious who it is that is going to be involved with this particular common property. Now really what that means in game theory terms is that it's clear who the players are. Who are the players and what are the payoffs? So clear boundaries are really tied to the fact that we can actually frame this in a game theory fashion. Secondly, we want to match the rules to local needs. What this really means is that we consider the well-being of the people that are involved with the agreement. That is, we need to take the payoffs into account. Third, those that are subject to the rules help make them. Now this is one way of really capturing the fact that we want local payoffs, or the payoffs of the players involved, to actually be what determines, right, the outcome. We're looking for what is the collectively best outcome, and the best way to ensure that is to have the people that are involved, right, in that collection, right, actually be involved with the process. Okay. Then we need some method for monitoring by the community members, and a way to punish rule violations. That's number 4 and 5. Right? So those two are really just connecting and saying we need to have some kind of enforcement mechanism that is actually possible. Right? We need to be able to identify when people break the agreement, and we need to be able to punish people that break the agreement. Some kind of reasonable means for conflict resolution. So this is something built in. This is actually a way of sort of building in a sort of repeated nature to the game. Right? So if you and I have a conflict, we have some sort of rule set up for how we work out that conflict, which usually is going to involve some kind of punishment reward strategy. Then ensuring that we have rulemaking rights, right, within the community. This is again very much like when we looked at points 2 and 3. It's about making sure the people that actually experience the payoffs are involved with determining what the enforcement mechanisms look like. And then finally, nesting smaller community management within larger community management. This is just acknowledging the fact that each community is part of a larger community, and when we think about what is collectively best, we need to think about not just, our small community, but about the larger community as a whole. And this is really also a way of making sure that outsiders, right, don't try to interfere too much with the small game that's being played by the local players. Right, so really, when you look at these, it's really kind of a way of thinking about how can we make an enforcement mechanism, right, for the players in this particular game. And that means that first we need to figure out who the players are and make sure only those players are there. We need to make sure we take into account the payoffs that they actually experience, and that they have some way to enforce, right, what is the best outcome, right, for the players involved. So now let's turn to thinking about cooperative game theory. Right. So here we're going to make a different assumption. We're going to assume now that enforceable agreements, right, to share any kind of costs or benefits are possible, right, if we make these agreements before the game starts. Right. So the focus then on cooperative game theory is a little bit different than with things like the prisoner's dilemma, what we call non-cooperative game theory. And that now we're going to focus on these two questions. First, what kind of coalitions would actually be possible? And secondly, how do they divide payoffs, right, between the players that are in that particular coalition? So you can see we've already kind of hinted at this with thinking about the possibility of enforceable agreements. Here, though, we are going to expand this and think about what happens if we have more than just two players. So one of the key concepts in cooperative game theory is the idea of the grand coalition. Right, so a grand coalition would be a coalition that involves every player in the game. Right, so really we're asking the question, right, is it possible for all of the players involved, right, whether they're 2, 3, 20, it doesn't matter, could they all get together and make an agreement that they would all want to abide by, where nobody has a reason to then, right, go out and betray or break off, right, from this agreement? Right, so really a lot of what cooperative game theory is about is figuring out if a grand coalition is possible in a specific case and what it would require to really make that happen. One thing that I would say, whenever you're looking at examples of a two-person prisoner's dilemma, it always has a grand coalition solution. Right? After all, there are only two people here. Right? It only makes sense to break off, right? If what is happening is not actually what is best for you. But generally, we can very easily, right, build in enforcement mechanisms, right? So with two-person prisoners' dilemmas, it's really kind of trivial to check whether there's a grand coalition possible. Right? But once we get to 3 players, then it starts to get a lot trickier. So let's go ahead and look at one of those tricky examples. Right, so what we have here, we have 3 players, A, B, and C. And what I have laid out here on your screen, right, is all the different sets of payoffs depending on how the coalitions form. Right, so the first 3, these are what each of the players would get if they were kind of stuck on their own. Right, so if player A is just all by himself, right, then player A would get 20. Right, on the other hand, if player B is by themselves, right, then they would get 40. If player C is by herself, then she would get 10. Right, so in this case, these are the individual payoffs. But if they start binding together, then they might have a better payoff. Right? So the value of a coalition between A and B, and first we'll go the two-person coalitions, which is the set here. If A and B are working together, then they can have a total payoff of 90. right? A and C working together gets a total payoff of 50. B and C working together would also get a total payoff of 90. Meanwhile, the Grand Coalition, right, working all together would get a payoff of 100. So then the question is, right, would this Grand Coalition be stable, and what would it take to make it stable? So first, let's think about each of the individual payoffs and how this plays in. So the question here would be, what is the minimum that each player requires, right, to be involved in the Grand Coalition? So here, we don't want to think too hard about this. Right? A knows that if they go off on their own, that's 20 that they're going to get. Right? Which means that if you want to convince A to be part of the Grand Coalition, you have to offer A at least 20 as their payoff. Right? Similarly, for B, they know if they go off on their own, they get 40. Right? So to convince them to be in the Grand Coalition, you have to give them at least 40. C, if they go off on their own, is going to get 10. Right? To convince them to be in the Grand Coalition, they have to get at least 10. Right? So the question then, is it possible, right, for us to have payoffs such that A gets at least 20, B gets at least 40, and C gets at least 10? Right? Well, add all this up, right, we would need at least 70 units, 20 plus 40 plus 10, right, in order to satisfy all of those demands. Right? Well, since the Grand Coalition has 100 units in its payoff, it can certainly pay a total of 70 to our 3 players. Right? So the possibility of just individually breaking off is not going to threaten the Grand Coalition. What about these payoffs? Right? So now we need to think about, well, what would keep A and B together, right, from just breaking off? Right? After all, if A and B together break off, then they would get 90. Right? Okay, that's pretty good chunk right out of that 100. If A and C broke off, they'd get 50, and if B and C break off, they would get 90. Right? Now what this ends up doing then is providing us with a maximum that is available for each player, given the possibility of these smaller coalitions breaking off. Right? So put another way, right, we know that total there's 100 available from the Grand Coalition, which means, right, if A and B can break off and get 90, we have to make sure that collectively, right, they get at least 90. Which means C then can't get any more than 10. Right? So at absolute most, we can only offer C 10, right? Because we have to save the 90 to be divided between A and B. Similarly, right, for B, right, in order to keep A and C from breaking off in this little coalition, we can't give B any more than 50. And finally, right, to keep B and C from breaking off into their little coalition, we can't give A any more than 10. So taking all of this information, right, from the minimum that each of our players needs and the maximum that we can provide them, and we find out is that the minimum payoff for player A is 20, while the maximum available to them is 10. That's a problem. Right? Because this makes it very clear that a Grand Coalition will not be possible. Right? We only have 10 available to give to player A. At minimum, they need 20 to be involved with the Grand Coalition. Right? So that means that in order to keep B and C in the Grand Coalition and give them that 90, A is going to be driven out of it. Right? They're just going to deviate and they're going to get 20 instead. Right? On the other hand, if we try to give A the 20 that they need to stay in the Grand Coalition, then this little tiny coalition of BC is going to break off, right? Because we would only be able to offer them 80, but they can get 90 if they break off on their own. Right? So it turns out a Grand Coalition in this game is not going to be possible. So then what about other coalitions, right? Might we possibly be able to have one of these two-party coalitions, right? So we could have A kind of working on their own and B and C working together, or B working on their own and A and C working together, or C working on their own and A and B working together. Right? So would any of these combinations be stable? Right? And if so, which ones would not be stable? And here the logic starts to get really, really tricky. Right? So certainly feel free to rewind and rewatch as necessary to get this. Right? Or you can also decide not to worry too much about the details of this specific example, but really just to get the idea of how the thought process. Okay, so let's think about that A-B coalition. Right? So thinking about that, right? So they can make an agreement, right? So when they make this agreement, we need to make sure that A gets at least 20, B gets at least 40, which means when we break it down, right, so they have 90 units in that coalition, right, A can get anywhere between 20 and 50, B can get between 40 and 70, and they'll be perfectly happy. Right, so we could split this 20-70, right, so 20 for A, 70 for B. B would be thrilled with that, A would be willing to go along with it, or A could get 20, and B could get or A could get 50, B could get 40, right? B would barely go along with it, but A would be thrilled, right? So somewhere in this combination. So somewhere between 20 and 50 for A and 40 and 70 for B. C, on the other hand, being left out of this coalition, only has 10, right? So what they would be willing to do, right, if they could make a coalition that involved them, they would be willing to pay A up to 40 to join that coalition. After all, an AC coalition gets 50, right? If C pays 40 to A to do that, then C is still left with 10, right? So as long as they're paying A no more than 40, right, then they would be willing to do that, right? Or if a BC coalition would be extremely powerful, right, they'd be willing to pay B up to 80 to join that coalition. Right? So what that means then, when we look at all of these numbers, is that there's really no way for the AB coalition to prevent C from bidding B away. Right? If C is willing to pay, say, 75, right, that's more than the AB coalition can give to B and keep A involved. Right? So B is going to get bid away into a BC coalition. What about the AC coalition? Would that be stable? Well, so consider AC. Right? So we know that they can certainly make an agreement as long as A gets between 20 and 40 and C gets between 10 and 30. Right? There are combinations here that will work, right, that they would both find acceptable. The question is then whether B could tempt either of them away. Well, think about B. Right? So B is earning 40 by themselves. Right? If they could form an AB coalition, right, they could get 90, or whatever their share of that is. Right? So they'd be willing to pay A up to 50. To deviate and hop into an AB coalition. Well, if they can pay up to 50 and A is only getting between 20 and 40, then they can certainly tempt away A, right? So we already know an AC coalition would not be stable. Similarly, B would be willing to pay up to 50 to convince C to join one, right? So B is one where if they form a coalition with somebody, it's going to be pretty high paying, and as a result, they're willing to pay quite a bit to break up this AC coalition. And as a result, they will tempt away either A or C. We don't really necessarily know which one, but certainly one of them will get tempted away. So an AC coalition would also not be considered stable. Right, so this is just this slide is just summing up the logic that we just went through on the previous slide, right? Pointing out that B, right, would be willing to pay A up to 50 to join an AB coalition, or would pay C up to 50 to join a BC coalition. And both of these numbers would be more than A can get or than C can get from the AC coalition. So B would bid either one of them away. Now finally, let's consider the BC coalition. I will say this is probably the trickiest one, right? So just walking through it, we know that they could clearly make an agreement, right? That 90 is enough, right? That B is going to get somewhere between 40 and 80, so they'll certainly cover the 40 they could get on their own. C would get somewhere between 10 and 50, right? So they will certainly get at least the 10 that they could get on their own. So the question then is it possible for A to tempt away, right, either B or C out of this coalition? So I want you to go ahead and think about that. I'll move forward here in just a few seconds, maybe pause the video, see if you can reason through it. I will say the reasoning on this one gets really tricky. All right, let's go ahead and look at the solution. Okay. Right, so we know, right, that A is going to be left with 20. Right, now they could pay B up to 70, right, to join an AB coalition instead. Right? So it looks like, after all, like B could get up to 80 out of the BC coalition, so it looks like they wouldn't be able to bid away B. Right? Or right, they would pay C up to 30, right, to join an AC coalition. After all, like an AC coalition would pay 50, right? A would need 20 of that, so that's 30 that they could offer to C. So again, it looks like a BC coalition, right, could pay more than those 30. The problem is this. Right? A stable BC coalition then would require that B would get somewhere between 70 and 80, right, to keep them from being bid away by A, and that C gets between 30 and 50 to keep them from getting bid away by A. It turns out that's not possible, because it's going to require at least 100 as a payoff to hit the minimum of 70 for B and 30 for C. Right? but there aren't 100 available, right, to the BC coalition. Instead, they only have 90 available. Right, so it turns out even the BC coalition, though it was the one with the best chance, it's not going to be stable either, right? A is going to find a way, like any way that they break up those 90 units between B and C, A is going to have somebody that they can approach with a deal that's going to make it worthwhile for them to make that agreement. So the prediction we would make based on all of this is that the Grand Coalition would totally fail to form, and that instead what we'd see are smaller coalitions forming, right? So A, B, B, C, A, C, but they wouldn't be stable, right? Whoever's left out would always find some way to tempt at least one member in the coalition out of it, right? So we'd see as kind of this rotation of coalitions that would form. That'd be the prediction about this specific case. One question you might want to think about is we know the Grand Coalition has a payoff of 100, but if you take just A by themselves and then a BC coalition that has a total payoff of 110, right, so might there be kind of some way, right, to treat this A plus BC as a Grand Coalition? And this would be a kind of a reasonable way to look at it. Now, it might be possible that as soon as these make an agreement, it might actually decrease their payoff, right? So that it isn't actually nonsense what we had before. But let's go ahead and reason through this just to check, right? So here's what we would need. What we would need is first that the total payoff would be 110, because that would be what would be available if we have the BC small coalition, right, plus A working by themselves. Then the individual payoffs, A has to get at least 20 for it to be worthwhile, B has to get at least 40 for it to be worthwhile, C has to get at least 10, and then also each of the sub-coalitions has to get at least, right, from any agreement they make, they have to get at least as much as they would get from making that sub-coalition. So A plus B has to be at least 90, A plus C at least 50, and B plus C at least 90. So let's reason through and see whether it's possible for us to come up with an A, a B, and a C payoff from this Grand Coalition that would actually be consistent with all of these restraints. So it turns out that if we have a total of 110 available, and we know that A has to get at least 20 and B plus C has to get at least 90, well then it's pretty clear, right, that A has to get exactly 20 and B plus C has to be exactly 90 as a total. Right? So putting this together, right, if A equals 20, and A and B together have to be at least 90, then B has to be at least 70. Right? And if A is 20 and A plus C together has to be at least 50, then C has to be at least 30. Right? So now we add all this up. So A is 20, B is at least 70, C is at least 30. That means we need at least 120 to make this stable. But we only have 110. Right? So even this kind of makeshift A by themselves, B, C coalition, that kind of Grand Coalition, this would not be stable. Right, so it turns out there isn't really a good way for us to get a stable combination. Right? Okay. So the big lesson that I want to pull from this is not all of these details about whether A, B, and C are going to form a coalition in this example. Rather, it's what cooperative game theory can do for us. Right? And that is, it can predict if a Grand Coalition would form and how the benefits would have to be divided in that Grand Coalition. Right? It can also predict for us if smaller coalitions would form, right, if they'd be stable, and how benefits would have to be divided within them for stability. Now, I will say as a general rule, any coalition, right, has to offer significant benefits beyond what individual actions would offer in order to be stable. Okay, so this would be a case where if we start out with something that looks like a prisoner's dilemma, often you'll find that you can have a Grand Coalition that comes together. Right, so this would be a case of something like the externality game. Right, so we can imagine, right, these two players, right, deciding, right, well, why don't we just form an agreement that we're each going to produce 6? Now, under cooperative game theory, right, the assumption, right, is that this would in fact be enforceable. Right, so the question then would be, would they be willing, right, to enter into this agreement? And, well, they know otherwise what would happen. Right? That is that they each end up with 800. Right, so we can reason through this with what I would call a complicated externality game. Right, so we imagine here 3 stages. Right, so first, any players who want to, right, can sign on to an agreement. Then what happens is that those that are inside of the agreement find what the best collective outcome is for those that sign on. And then in the third stage, those who didn't sign on follow whatever is in their own individual best interests. Now, an important thing about this is that those inside of the agreement when they're thinking about stage 2, they know what's going to happen in stage 3. That is, that those who didn't sign are going to follow their own best interest. So they'll take that into account. So it might be that there's a way that those inside of the agreement can still have an impact on those outside of it. Okay. Right, so in this case, kind of reason through it in this way. Right, so we know that if both polluters sign, then they would decide what is collectively best, right, is that they would both pollute 6 units. They each would have a cost of 720. That is the best collective outcome for them. Right? If both polluters sign, then we also don't have to worry about like what are the people that aren't polluting that aren't signing going to do, because there isn't anybody. Well, if one polluter signs and the other doesn't, right, then we know that whoever the non-signatory is going to pollute a unit at 10 units. But if that's the case, right, then it's in the signatory's best interest to pollute themselves, because in this case, if there's only one person signing, they're effectively just pursuing their own best interest, right? So it turns out everyone pollutes. It's an $800 cost for everybody, right, just as if nobody signed. So in stage 1, we'd end up with something like this. Right, so the decision to sign or not, right, if both sign, then they have costs of 720 each. If either of them doesn't sign, and if they both don't sign, then it turns out the cost is going to be $800 each. Right, so it turns out that you would have a reason to sign as long as you think there's any possibility that the other party might possibly sign. It's also true that not signing, right, is never going to help you. Right? Signing can help, and it can't hurt. Right? So for that reason, we would expect both of the polluters would be willing to sign most likely. Now what if we have 3 polluters? Now things get a little bit more complicated. Right? So again, we're going to assume that each polluter has a cost, right, of the total amount of pollution squared, right, so that's the damage being done by the pollution, plus their own abatement cost. So again, right, 30 minus, right, whatever their own pollution level is squared. Now we know that if we just have one person, they would have an incentive to sign, right? They would want to sign as long as there's any possibility somebody else might, right? So if one has already decided to sign, does it make sense, right, for a second to sign? Now, I will say the logic here does get a little bit tricky, so kind of do your best to follow along. Right. So first, the result of just one signatory. Right? If only one person signs, then they all act, right, really as if nobody did. Because if I'm signing to do what's in my own best interest, I would do that anyway. Right? Well, it turns out the individual best responses in this case are given by this formula. Right? So that is that what player 1 decides to do in terms of its pollution is 30 minus player 2 minus player 3, and then we divide that by 2. And we get a very similar outcome for both player 2 and for player 3 as well. Right, so when you have the system of 3 equations, what you find out is that they will each pollute 7.5 units. So we have an individual cost then of $1,012.50 in this case. Right, so then what happens, right, if we have one person signed, the other 2 didn't, right? Well, what if then a second person thinks, well, maybe I should sign? In that case, the coalition knows that the third polluter, right, so let's say polluter number 3 is the one that is definitely not signed at this point, they're going to create pollution according to the formula that we just saw, that is 30 minus the total amount of pollution produced by the other 2, and then divide that by 2. Right, so the coalition will take that into account in their own calculation. Right, so the coalition's cost then will be, right, whatever the amount of total pollution is from the coalition plus 30 minus that total coalition divided by 2, right? So that would be the amount that the third polluter decides to pollute, right? Take that whole thing, square and double it to account for both the accelerating costs of pollution and also the fact that there are 2 parties now in this agreement, right? Then add on the abatement costs for each of those that have signed, right? Well, the result you get out of this, interestingly, is that, again, everybody creates 7.5 units of pollution, right? So 2 people out of the 3 signing the agreement is basically the same as only 1 signing it, which is basically the same as nobody signing it, right? So there's really no reason not to go ahead and sign, right, if you think that nobody else is going to sign it, or if you think there's even one person that's not going to sign it in this example. So put another way, there's no reason not to join. So let's consider what happens if the third considers joining this agreement. So we've already figured out that any 2 of our polluters have no reason not to just go ahead and join. So does the third have a reason to go ahead and join, or would they have a reason to stay out of it? Right, so let's consider, right, if they're all three in on it, then in that stage 2, right, they would consider what is the collectively best outcome for them. Right, so I have here what the problem would be. If you want to work out the calculus, you're certainly free to. You're also certainly free to use whatever method you want, or guess and check, what have you, to try to figure out whether this is true. But here's what I came up with. Right, so remember the total cost of the pollution damage done would be what it is for each firm, so total pollution squared, but then you have to include the fact that there are 3 firms, so multiply that by 3, and then we add up all of the abatement costs from each of our 3 polluters. Now, when we choose the levels of pollution that would minimize that total cost, what we end up with is that each polluter will pollute the same amount, and that is 3 units. Now, this is a significant difference. In fact, it's way less than that 7.5 than what we saw in the previous cases. So if we have nobody signs, if one person signs, 2 people sign, all the same results, we're all going to create 7.5 units of pollution. Once the third signs, now it makes sense for us to only pollute 3, right? Cut pollution more than half. Now, if we do that, the cost for each of us is going to be 810. Where we saw earlier, the cost, if nobody signs, is going to be $1,012.50. And so it looks like if the other 2 have already signed, then I do want to be the third one to sign. It's going to save me $200 to do that. After all, my signing, right, will convince, well, not only am I committing that I'm going to pollute less, but very importantly, I'm committing them to pollute less. Right? And that is where the big benefit comes from, is that by signing on, I've changed the behavior, right, of other people that have an effect on me. Right, so there's no reason not to sign for anybody. Everybody has a good reason to sign if they think everybody else is going to, right? So it ends up, we would expect everyone to, in fact, be willing to sign and to create this good outcome. So the end result is that we would expect polluters to sign the agreement as long as there's any chance, right, that the others are going to sign as well. Right? And even if there is no chance the others are going to sign, there's no reason not to, right? So it might be that there's some kind of external things we're considering, not just the cost of pollution itself, right? So maybe if you just feel good about signing this agreement, even if it doesn't do anything, right? Similarly, on the flip side, right, the big reason someone might have not to sign this agreement is if there's some kind of external thing they're concerned about other than the cost of pollution, right? So maybe not being a part of it makes you feel good about yourself. Right? So that would really be kind of something else we'd have to take into account. But if we're only considering the cost of pollution itself, right, then we'd expect, at least in this case, that everyone is going to sign on. Now, one thing I will say, this case is a very simple one, and it gets complicated by the third polluter being there, but it's simple in the fact that we're only dealing with cases where the polluters are all identical. Right. Things can get a little bit trickier when, say, we have different costs of abatement for different polluters. That can make the case a little bit harder to work with. Right? So certainly feel free to look in your textbook. Your textbook has an example of this with just 2 players, but where there would be differences in what their abatement costs would be and what their payoffs would be. Right? So you can look at examples there. In that case, you would see more of kind of the cooperative game theory coming in with the idea of side payments. Right, so if you have somebody that benefits a lot from signing the agreement and somebody else who really doesn't benefit, but the collective is better off, what you'll generally find is that those who benefit a lot would be willing to pay something, right, in order to convince those who would not necessarily be better off to go ahead and join. Right. And so this is just kind of a note of that. This example is a symmetric one, that is, all of the polluters are identical. Certainly feel free to check the chapter for an example where there's asymmetry. So let's finish up with just a few takeaways. First, with environmental issues, people will often have an incentive to act against what is the collective best interest, but there are a number of ways to try to fix that issue. Right? Like we have enforceable agreements, so that's where cooperative game theory would come in. We have long-term relationships as a possibility, so the idea of repeating a game over and over. Right? Simply punishing bad behaviors and rewarding good behaviors, right? So the idea of tit-for-tat as a strategy in a repeated game. And cooperative game theory is really built around how do we make enforceable agreements that we would in fact all benefit from, or if we get kicked out of that agreement, we're actually made worse off, right? So all of these ideas, right, come in and help us to solve, right, what looks like a prisoner's dilemma to start. Another thing that I think is important for us to remember is that people are creative problem solvers. That is, if people recognize that there is a problem, right, we will generally try to take steps to solve that problem. Right? When we see problems, we do try to solve them. And I think that's really the idea behind Ostrom's principles, is that if we give people a framework in which they can solve problems themselves and start enacting some of these things that we have here on this slide, start making these enforceable agreements, have ways for them to monitor each other's behavior and make rules that actually make sense to them as a community, then we will actually generally do a pretty good job. Right? So one of Elinor Ostrom's big points when she laid out these principles was that she really believed that all the claims that game theorists were making, that there were just all of these prisoners' dilemmas all over the place and we had a bunch of awful outcomes, right? She didn't believe that was the case, because she believed that people are creative problem solvers, and that they can, in fact, right, solve these problems themselves as long as they're given a framework in which to do that. Right? So that's the idea of Ostrom's principles, and I think one of the big takeaways of game theory is to figure out what are the conditions, right, that Ostrom lays out for us, right, in which people can, right, solve what looks like a tricky problem, nonetheless people find ways, right, to solve these problems.